The supersymmetric constraint is quite strong, so this can determine the specific theory or model. Later we talk about the SQCD, the supersymmetric quantum chromodynamics. SUNC gauge theory can be highly constrained by the holomorphy and the symmetry condition. And today we talk about some generalizations of this SQCD with the pre-parameters of N app, the number of step label, and the NC, the number of the color. The holomorphy was that the superpotentials only depends on the color superfields, not by the its complex conjugates, and the loop corrections can be protected by the non-normalization theorem. And the SQCD is consisted by the SUNC gauge theory with an up labels of the cork superfield Q and its conjugate Q tilde. Then the theory includes the global symmetry of the SU and up, left-handed and right-handed, and the U1B barrier number, the U1R as the R parity. And this global symmetry strongly constrains the dynamics. The gauge invariant operators are given by the meson and the baryon and antibaryon. And by using the condition of the holomorphy and the symmetry, the exact non-perturbative superpotentials are given for the large NC compared to the NAP. This is called the ADS superpotential. And the index and the coefficients, the functions of the NC and the NAP, and in the denominator there is the determinants of the meson operator. And this ADS potential do not have the vacuum, it only has runaway vacuums in the spatial infinity. So to make the stable minimum, one can add the cork mass term like as a color perturbation theory. And this stabilizes the vacuum and allows the vacuum expectations values of the stability. And also we consider that the special case of that the NF is equal to the NC. Then the classical moduli path is modified quantum mechanically with the right hand side. And these conditions removes the origin and the vacuum structures becomes non-trivial. So this is a review on the previous discussions on the advances supersymmetry. And today I will turn to the other case of the relation between the NAP and the NC. So later we talk about the NC is rather than NAP, and the NC is the same with NAP. Then how about the NAP is rather than NC? Especially the NAP is equal to the NC plus 1. This gives the s-confinement behavior. The IR theory is completely determined by the gauge invariant operators like as the meson and the baryon. And there are no remaining gauge degree of freedom. This is called the s-confinement. The dynamics is exactly and uniquely determined by the following superpotential. So here, again, all the degree of freedoms are described by the baryon and the meson operator. Let's think about ordinary QCD with the non-supersymmetric theory. There's also the confinements that are expected, so when the theory is lower than the 100 ANIB, the QCD confinement scale. But the IR theories are not explicitly known. We don't know the exact theory. One cannot write the complete effective Lagrangian in terms of the hadron, and the coefficients is undetermined and not unique in such a color perturbation theory in the non-supersymmetric QCD. But if you consider supersymmetric QCD is partially NAP equal to the NC plus 1, the IR theory is fully determined by the meson, baryon, and antibaryon operator. So we can determine the exact and the unique superpotential. So the strongly coupled dynamics can be exactly solvable in the IR limit. In the UV theories that are given by the gauge theory with acid answer with the Cork superfield. And now the IR theories that contains the no gauge interaction, but there is a meson baryon antibaryon in the superpotential. So this represents the complete change of the variable from the Cork, anti-Cork superfield, and the gluon to the meson baryon and antibaryon operator. So now we have the overall behaviors of the supersymmetric depending on the number of the fiber of the cork and up and the number of the color for the gauge theory. When the NC is larger than the NUp, the superpotential is given by the ADS bomb, which have the runaway vacuum, and we should add the cork mass term. And when the NUp is the same to the NC, it gives the strong conditions. And this is the modified quantum mechanics in the right hand side. And the one that NUp is equal to the NC plus 1, then also we can determine the IR theory of the superpotential. And the one that NUp is larger or equal to the NC plus 2, then we don't have the no simple description with the confinement operator. Unlike the case of the NUp equal to the NC, there are no quantum constraints on the modular space. And the space of the vacuum is smoothly and the parameters by the all the confinement operator. So the NUp equal to the NC plus 1 case can give the complete and regular IR effective theory. This case satisfies all of the following one: the confinement, and there's a no mass gauge boson like gluon, and the IR described by the gauge invariant confinement operator, and the modular space is smooth, and the superpotentials that exist which satisfying the locality. So this combination is both as confinement and quite complete regular unique and exactly determined behaviors can be obtained by such a strong case. Now I turn to the next case. If the NUp is the largest or equal to NC plus 2, then the descriptions of the meson and the baryons are broken down. This corresponds to the number of the fibers is very large. And there are no superpotential form which is consistent with the condition of the symmetry and the holomorphy. The modular space of the vacuum expectation values of the cork and anti-cork field can be described, and the color fields is given by the with the degree number of the freedom of the NC times the NUp. So if we estimate the dimension of this space, the dimension of the gauge group as the NC is NC squared minus 1, the number of the generator for the Cn, and we can estimate the configuration space by the gauge transformation. So the original degree of the freedom is the NC times NUp times 2, because there are two cork and the anti-cork field, and we should subtract the gauge redundancy, the number of the generators. So the dimensions of the modular spaces are given by the 2 NC NUp minus the NC squared minus 1. So if the NUps increases, the dimensions of the modular space grows. So the modular space becomes large when the NUps increases. So for the large NUps, the relations between the confinement operators becomes highly nonlinear and very complicated. So the relations are not independent, so that this cannot provide the complete set of IR degrees of freedom. So the IR theories requires a new description, which is realized by the Seiberg duality. So now let's talk about the NUp is smaller than NC plus 2. How can we describe the IR theory? We can introduce the electric strong theory consisted by this cork and the anti-cork superfield. Yeah, and the Seiberg duality states that the theory is equivalently in IR to the magnetic weak theory. So there are duality between the electric strong theory and the magnetic weak theory. The electric strong theory is described by the SC gauge theory, but the magnetic weak theory is described by the SC minus NC gauge theory. This magnetic theory contains the dual Kirk field, small q, and this is the charges around NF minus NC, the burst one. And this makes the gauge singular meson field. This magnetic weak theory is not additional theory introduced on the this electric string theory. Rather than that, it is just alternative UV description, but giving the same IR physics. So there are two different UV theory, which is the SUNC for the electric strong theory and SU minus NC electric weak theory, and this gives the same IR physics. The RG flows eventually gives the same IR fixed point. So again, the variables of the confinement operators cannot provide proper descriptions of the modular space in the IR theory due to the complicated algebraic constraints and independent relation. So there is no locally effective theory. But if we introduce the magnetic weak theory, then the new degrees of freedoms appear, the dual core, small q and q tilde. And this can provide the additional condition for the potential, and the relations becomes dynamically. So the complicated constraints of the electric descriptions can be replaced by the such a new degrees of freedom, and we can obtain the effective theory in the IR. But to make the same IR physics for this electric and the magnetic theory in the UV, we should impose the operator matching condition. In the electric theory, the gauge invariant operator is the meson field, but in the magnetic theory, the meson fields are introduced as independent gauge singular fields, not the composites. So the we can match between the meson operators, which is consist by the two Kirk field, and the meson operators in the magnetic theory, but that just the gauge singular field is not composite field. So there is a matching between the two meson field in each theory, and also for the baryon operator. For the electric theory, baryon operators consist by the NC times of the Kirk field. But in the magnetic theory, the baryon operator is given by the NF minus NC numbers of the dual Kirk. So we can match this between the two baryon operators in the electric theory and the other baryon operators in the magnetic theory. And also the consistency further requires that the modular spaces becomes the same. It's partially the constraints that's given by the length of the meson operator is smaller than the NC to reproduce the magnetic theory by the upstem condition, and giving the eventually the same vacuum structure. So if you consider the following superpotentials in the magnetic theory, the meson singular and the Kirk, dual Kirk in the magnetic theory, then the equation of the motions can be derived for each field. Meson singular, dual Kirk. Then by using them, we can obtain the relation between the length of the meson singular and the number of the color. Because the last two conditions implies that the column of the Kirks, dual Kirks, and is the anti-dual Kirks, should lie in the corner of the meson singular. This is just a linear algebra. And since the dual Kirks carries the gauge index of the magnetic theory, so there's enough minus NC independence vector satisfying this linear equation. So the dimensions of the kernel space of the Mason singular should be the larger also same to the n of minus NC, and by using the dimension theorem in the linear algebra, we can obtain the length of the arm just smaller or the same to the NC. So that there is the relation to reproduce the same modular space in the IR theory from the magnetic theory compared to the electric one. So based on this Seiberg duality between the electric and the magnetic theories, we can evaluate the RG behaviors to obtain the IR fixed point from the UV model. The one-loop coefficients are determined by the NC and NF. The first one for the coefficient of the beta function for the electric one, and the second one is the magnetic. And now the this paths are replaced by the NF minus NC. And in the lenses of the following inequality, this is called the conformal window. The both theory have the same flow to the IR fixed point. In this interval, the theory, neither theory is free, but the one can describe the weakly coupled theory near the edges of the window. So, for example, if the NF is the near to the 3NC, this inequality, the electric theory is the weakly coupled because the B cell becomes a small, but the magnetic theory is strongly coupled because this B0 magnetic coefficient that becomes large. But if the condition satisfies the NF is near to the derivative 2NC, then the electric theory has the large coefficient, so it has a strongly coupled, but the magnetic theory becomes a weakly coupled. So in this conformal window, both beta functions are positive, but the magnetism of the coefficient determine which side is weakly coupled. So the depending on the NF size near to the upper inequality, so lower inequality, the strongly coupled systems, the quite different, and this allows the strongly coupled dynamics can be described by the dual weakly coupled descriptions. So we talk about the SUNC SQCD with NF nebulizer, and is the IR dynamics, and we consider the various situation, ADS per potential, the moduli space, and s-confinement today, and for the large enough case, this cannot describe the effective series in IR due to the large degree of freedom. So that we introduce Seiberg duality with the additional magnetic descriptions on the UV theory with NF minus NC gauge, and this introduced the dual quarks and the Mason singular, and we matches the operators and modular space to have the same IR fixed point. And this duality is realized in the conformal windows, and depending on the NF, whether it's located in the upper edges or lower edges, the electric magnetic theories that we curve through the strong coupled dynamics and vice versa. So the Seiberg theory can describe the IR theory in this such a large enough case. So we talk about some generalizations of the SQCD and especially the Seiberg duality.